In this video, we'll finish talking about applications of aqueous equilibrium by looking at precipitation reactions and selective precipitation. Okay, so let's talk about the precipitation condition. So let's look at calcium carbonate. We have this equilibrium and an associated KSP, and we know that we can find the molar solubility of this. So let's think about what Q would be in this circumstance. So Q, remember, is the same expression as K, but instead we plug in the values that we actually have. So let's look at an example. So let's say we had a solution that was 5 times 10 to the negative third molar calcium and 4 times 10 to the negative 2 molar carbonate. And so put all these things in all at once and then decided whether or not we'd see a precipitate in this reaction. To do this, we could plug these values in for Q, so we're not at equilibrium yet, and see what we get. So if we plug these in, we'd get 5 times 10 to the negative third times 4 times 10 to the negative 2, which is equal to 2 times 10 to the negative fourth. So this value of Q does not equal the value to K. And specifically, we have that Q is greater than K. If you recall back in equilibrium, if Q is greater than K, this means we have too many products or not enough reactants. And in this case, that means too many things are dissolved. And so the reaction will go back this direction and form solid. So generally speaking, if you have the KSP expression and you calculate Q, if K is greater than Q, no precipitate will form. All the ions that you have in solution will stay in solution. But if Q is greater than K, you'll go backwards and you'll get some solid from your solution. Let's look at another example of this. So say we mix a solution that is 150 milliliters of a 1.0 molar magnesium nitrate with 250 milliliters of a 1 times 10 to the negative 1 molar sodium fluoride. And we want to find the concentration of magnesium and fluoride that we have at equilibrium. We're given the KSP for the solid that can form between magnesium and fluoride. We could see the other ions we'd get. So if we list the major species, we'd have magnesium, nitrate, sodium, and fluoride. So these two ions, these major species, sodium nitrate, those won't make a precipitate. So we know the only solid that we can get is this magnesium fluoride. And so what we'll do for this, first we'll determine to see if a precipitate will form. If no precipitate forms, then the amount of magnesium and fluoride that we have in solution will stay the same. If a precipitate will form, then we have to run the reaction to completion to see how much solid will form, and then use an ice table at the end to find the final concentration. So to determine Q, first we need to find the concentration of everything. So for the concentration of magnesium, we're going to have to use this equation for making dilutions that we learned in a previous chem class. So we'll start with our initial concentration of magnesium and its initial volume, and that would be equal to the final volume, since we're adding these two solutions together, times its final concentration. And this gets us a final concentration of magnesium. That is equal to 3.75 times 10 to the negative third molar. If we do the same thing for fluoride, we get a concentration of 6.25 times 10 to the negative 2 molar. So to calculate Q, we'd need the equilibrium expression for this reaction. Since we have 2F minus, that would mean that Q is equal to the concentration of magnesium times the concentration of fluoride squared. Plugging in our numbers before, this gives us 3.75 times 10 to the negative third times 6.25 times 10 to the negative 2 squared. And this is going to be equal to 1.46 times 10 to the negative fifth. This value of Q is greater than the value of K. So that means a precipitate will form. And we need to figure out how much of this will form. In order to do that, we'll do this stoichiometry problem. So in order to do this, we need to look at the reaction that we're going to be doing. Again, we have our magnesium and fluorides that are going to make the solid. And since it's a stoichiometry problem, we need to convert everything to moles. So for magnesium, it's going to be the volume times the concentration. And same thing for fluoride. And for these, we're going to have to find out which one's the limiting reagent. So what we can do is we can calculate how much magnesium fluoride could be made from both. So if we start with just the magnesium and we look at the stoichiometry, that's a 1-to-1 ratio. So for every magnesium, we make 1 magnesium fluoride. And so based on the magnesium, we'd make 1.5 times 10 to the minus 3 moles. If we're looking at just the fluoride, since we need 2 fluorides for every magnesium fluoride, this means we would make 1.25 times 10 to the negative 2 moles. And since we make the least with magnesium, this makes magnesium our limiting reagent. So now we need to find the concentration of everything after we form the precipitate. We can use a version of the before and after table for this. So we start with 1.5 times 10 to the negative third moles of magnesium, 2.5 times 10 to the negative 2 moles of fluoride, and no moles of the magnesium fluoride. Since magnesium is the limiting reagent, that's how much we're going to use. And we're going to use twice that since there's 2 fluorides per magnesium of the fluoride. And we're going to make that much of the magnesium fluoride. So after we run this reaction, we'll have no magnesium left. 2.2 times 10 to the negative 2 moles of fluoride left, and 1.5 times 10 to the negative 3 moles of magnesium fluoride. Okay, so this is what happens when we form the initial precipitate. So this is the second step and what we end up with. So we end up with some fluoride and some of the solid. We can't make any more of the solid since there's no more magnesium to make it. So now what we found after we did the before and after, but just like when we saw the equivalence point with a titration, we now have 0 on one thing at the end of an equilibrium, so we have to do one last equilibrium problem to find the final concentration of everything in this solution. So first we'll set that up. And remember, we won't care how much of the magnesium fluoride we have now, because it doesn't show up in the equilibrium expression. We don't have any of the magnesium left. We have the fluoride. The value that we have here is moles, but we need a concentration. So we have to divide by 0.4 liters, and that gives us 5.5 times 10 to the negative 2 molar, since the ice tables always have to be in concentrations. Since there is a 0 on this side, we know we're going to make a little bit. But since we just formed this precipitate and we know this K value is small, we know that X is going to be small. So at equilibrium, we can use the small x approximation and get that we'll have X of magnesium and 5.5 times 10 to the negative 2 of the fluoride. The last thing is to set this equal to the KSP, and that's X times 5.5 times 10 to the negative 2 squared. And solving for X, we get X is equal to 2.1 times 10 to the negative 6. And so we have the concentration of X, which is magnesium, the concentration of 5.5 times 10 to the negative 2, and that's the final concentration of all these species at equilibrium. The last thing we'll look at is selective precipitation reactions. And this is a case where we have a solution. So say here we have something with some copper and some lead in it. And we're going to add iodide to this reaction. Now, lead iodide and copper iodide are both fairly insoluble with 2 different KSPs. Because these aren't equal, what's going to happen is we add the iodide. Each individual one will precipitate again when Q is greater than K. And so what we can do to see which order everything will precipitate in is find out how much I we can add before Q is equal to K, and then compare these to see what the actual precipitate will be. So for lead iodide, we know that KSP is going to equal to the concentration of the lead times the concentration of the iodide squared. And we're given the initial concentration of the lead. And if we solve for X, we get X is equal to 2.65 times 10 to the negative third. So this is telling us the concentration at which we'd get lead iodide from the solution would be when we add enough iodide to get 2.6 times 10 to the negative third or higher. For the copper iodide, we'll have 5.3 times 10 to the negative 12th is equal to the concentration of copper ions times the concentration of iodide ions. And we know the concentration of copper, and we're looking for X. And if we solve for X in this case, we get that it's equal to 5.3 times 10 to the negative 8th. So what this is saying is that copper iodide will precipitate when the amount of iodide is 5.3 times 10 to the negative 8th, and lead iodide will precipitate when it's 2.65 times 10 to the negative third. Since this value is bigger, that means as we add iodide to the solution, copper iodide will precipitate out first, and that'll precipitate when we add enough iodide to get to a concentration of 5.3 times 10 to the negative 8.